After a journey of 1.5 million kilometers, the James Webb Space Telescope arrived at the L2 point of the Sun-Earth system. It achieved this by performing its final mid-course correction burn, the so-called MCC2. It lasted only 297 seconds, just under 5 minutes, and changed Webb's speed by about 1.5 meters per second. That's about the pace of a brisk walk. It may not seem like much, but it was enough to put Webb into orbit around L2. And it wasn't just any orbit, it was a huge orbit, more than twice the size of the Moon's orbit around the Earth. Webb takes about 6 months to complete a single orbit around L2, and that first orbit is packed with mirror alignments, phasing, instrument calibration, moving target tracking tests, checks, and orbit maintenance maneuvers. And finally, the first scientific observations. But what exactly makes L2 so special? I mean, it's just a point in space and an empty point at that. So, how can Webb orbit something that's not even there? Well, it's true that L2 is empty, but orbiting empty points in space is actually quite common. This happens because whenever two massive bodies orbit each other, both bodies revolve around a common center of mass, the barycenter. If the objects are massive enough, this center of mass is located somewhere between them. We only say that the Moon orbits the Earth because this center of mass is inside the Earth. But Pluto and Charon have similar masses, so their barycenter is at a point in space between the two. In other words, the fact that something can orbit an empty point in space isn't that strange. But that's a two-body system and still doesn't explain how the Webb can orbit a point that's outside of a two-body system. The good news is that we can break down this problem and really understand what the L2 point is and how the Webb orbits around it. In fact, several spacecraft have already orbited L2, like NASA's WMAP satellite and ESA's Planck and Herschel telescopes. Russia's Spectre-RG and ESA's Gaia are orbiting there right now. L2 is one of the 5 Lagrange points between the Sun and the Earth. Actually, these 5 points exist around any two-body system. There are Lagrange points for the Earth-Moon system, a set of points for the Sun-Jupiter system, and so on. If a third object is placed at any of these points, the gravitational forces of the two large bodies combine in such a way that they keep this third object stable in relation to the others. In practice, as the system orbits, the third body goes along for the ride. That's why the L1 point of the Sun-Earth system is great for missions that observe the Sun, like the Solar and Heliospheric Observatory, and for missions that observe the Earth, like DSCOVR. Similarly, L2 is the right place for astrophysics missions like Gaia and Webb. At both points, the spacecraft maintain a constant line of sight for communication with Earth, even as Earth orbits the Sun. But L2 is especially important for Webb because there it can block the heat from the Sun, Earth, and Moon with a single sun shield. It's the perfect place for infrared astronomy. But there are some important caveats. The first is that the third object needs to have a mass that is very small compared to the larger bodies. That, of course, isn't a problem here. The mass of Webb is negligible compared to Earth, and even more so compared to the Sun. The other caveat is that the Lagrange points are, at best, metastable, especially the first 3. To understand what this means, imagine a perfectly smooth and frictionless saddle. Now imagine trying to balance a marble right in the center of that saddle. It's theoretically possible, but in practice it's extremely difficult. The L2 point is similar to that. An object that moves perpendicular to the Sun-Earth line slides back to the center. But then it ends up falling, either toward the Earth or to the opposite side. And if Webb falls to the opposite side away from Earth, it's in real trouble, because the only way to bring it back would be to turn the spacecraft around and fire the engines in the opposite direction. But that would make the telescope heat up suddenly. All the structures would expand, glues and adhesives would melt, and the mission would end right there. And that would be terrible. Webb only has thrusters on the hot side facing the sun. That's because hot thrusters would contaminate the cold side of the telescope with heat or with combustion exhaust or fuel that would end up condensing on the optics, which would also be terrible. A safer approach is to place Webb almost at L2, but not exactly on it. That way, when it starts to fall back toward Earth, a tiny burn from the thrusters pushes it back near L2 almost, but not completely. This way, Webb never runs the risk of falling beyond L2 from where it couldn't be recovered. And that's why the Ariane 5 launch was purposely designed to fall just short of the target, leaving the spacecraft itself to perform a series of mid-course correction burns. The first two, MCC-I and MCC-1B, were carried out on the way to L2. But arriving just before L2 brings another problem. At that distance, if Webb were exactly at L2, the sun would be in a permanent annular eclipse because of the Earth. And Webb runs on solar power. It could use nuclear power, but that's expensive and complicated. Another complication is that Coriolis forces would make Webb librate around L2. In other words, it would find itself in a small orbit around the point, which would require even more thruster burns to control. And the moon's gravity on Webb also still applies, and it changes all the time as the moon orbits the Earth. It turns out that all these real-world complications can be solved in a simple way. By putting Webb in a large orbit around L2, how can you orbit something that isn't there? L2 is still an empty point in space. To better understand, it's worth looking at the problem by considering some of the forces acting on Webb. If Webb were exactly at L2, it would feel gravitational forces from the sun and the Earth. So, let's draw these two forces separately to keep track of each one. Since Webb also orbits the sun at the same time, you can imagine a centrifugal force pulling Webb in the opposite direction. The beautiful thing about L2 is that, at that distance, the centrifugal force is exactly balanced by the combined gravity of the Earth and the sun. You may have heard that centrifugal force doesn't really exist. And that's correct, but here we're talking about a rotating reference frame, not an inertial one. So, centrifugal force is still a useful way to sum up all the real effects at play. And to keep things simple for now, let's ignore the effects of the moon's gravity and the fact that the sun and the Earth are not points, but extended bodies. Now let's move Webb a little bit up, away from L2. The gravitational force from the sun changes very little because it's more than 150 million kilometers away. But the Earth is only 1/100th of that distance away. So, its gravity changes a lot. Since the Webb is now farther from the Earth, its pull gets weaker. And it also stops being parallel to the direction of the sun. So you can break this force into its X and Y components. Then the problem seems clear. The centrifugal force points in the X direction of our diagram, but now it's greater than the combined gravitational forces of the sun and the Earth, meaning Webb will drift both downward and farther away from L2. So, it's necessary to correct this drift in both directions, X and Y. First, we bring Webb a little closer to Earth so that it hovers over a new point, which we'll call L2 prime. Earth's gravity becomes stronger, and its X component once again balances the centrifugal force. But the Y component also became stronger. So, Webb tends to move downward. And the closer it gets to the Sun-Earth line, the stronger Earth's gravity becomes and the more it gets pulled closer. That can't happen either, because then the heat load would become too strong for the sun shield to handle. But you can counterbalance that downward force by giving Webb a push to the side, into the screen. This creates a new centrifugal force, which balances the downward pull of Earth's gravity. Combined with that sideways motion, Webb starts to follow a new circular orbit, a halo orbit around L2, and that means there doesn't need to be any mass at L2 to attract Webb. In fact, Webb is only being pulled by the Y component of Earth's gravitational force. It's worth mentioning that this is a very simplified description of Webb's orbit around L2. Real-world complications have been deliberately left out, just to make it clear how Webb is able to orbit something that isn't actually there. But putting Webb in its actual orbit required taking all those complications into account. To make things easier, Webb wasn't launched exactly to L2. Instead, it was launched to a point next to L2. As it started to fall, Webb performed the MCC-2 burn to settle into orbit. Since part of that initial descent was pointed in the X direction toward Earth, the burn put Webb into an orbit that's now tilted at about 33 degrees. The orbit isn't perfectly circular either. It's elliptical in shape. Because of this, Webb's distance to the L2 point varies between 250,000 and 832,000 kilometers. To give you an idea, the Moon's semi-major axis is about 400,000 kilometers. So Webb's orbit around L2 is gigantic. This large orbit was chosen because it makes it much easier to reach L2. The farther something is from the focus of its orbit, the slower it moves and the less energy is needed to maneuver it. That's why a 5-minute burn and a delta V of 1.5 mass were enough. The large orbit also ensures that Webb will never enter the shadow of the Earth or the Moon during the mission. On the other hand, larger orbits can let scattered light from the Earth or the Moon pass by the edge of the sunshield and reach the primary or secondary mirrors. In addition, a larger orbit can reduce the number of communication windows with the Deep Space Network. That's why Webb needs to change its orientation to keep scattered light away from the mirrors at all times and schedule communication links accordingly. Webb takes about 6 months to complete one orbit around L2, even though sometimes it moves a little beyond that point. The geometric center of the orbit remains over the L2 point on the Earth's side. Remember, we don't want the ball right in the middle of the cell. That's why Webb performs small orbit maintenance burns from time to time to preserve its trajectory. Missions like Gaia only need 3 to 4 of these burns per year, but Webb needs a lot more for a few reasons. First, its sunshield constantly experiences torque caused by solar radiation pressure. Webb can counteract this rotational force by accelerating its reaction wheels. But the solar radiation pressure is relentless, so the wheels need to spin faster and faster over time. At some point, a maintenance burn is needed to reposition Webb and let the wheels slow down again. Webb also changes its orientation when pointing from one position to another. All these movements disturb the orbit a little bit, requiring more maintenance burns. And that's why Webb performs a burn every 21 days. The exact timing and duration of these burns are calculated by the flight dynamics team at NASA's Goddard Space Flight Center. They do this by monitoring Webb's telemetry data and using tracking data from the Deep Space Network to precisely locate the spacecraft's position and movement at all times. They even take into account the gravitational disturbances from the Moon and the other planets in the solar system. It's meticulous work that will last for the next 2 decades of the mission. And maybe that's the most beautiful thing here. Webb doesn't orbit a star or a planet or anybody you can point to in the sky. It circles around an empty point, a place where nothing exists except for a delicate balance of invisible forces, a point that is only something because the gravity of the Sun, the Earth, and the movement of its own orbit cancel each other out there with just the right precision. Orbiting nothing in the end is one of the most elegant ideas in celestial mechanics. Your stomach is already in your throat. You know the moment. The elevator that drops 2 floors before it stops. The roller coaster drop when the car goes over the top, and for half a second your body forgets what weight is. That moment, that shiver of free fall that lasts less than a second in your life, is right now the permanent state of those who are 400 kilometers above your head. They're not floating because they've escaped gravity. They're floating because they're falling. Really falling at almost 7.66 kilometers per second, over 27,000 kilometers per hour for more than 2 decades without stopping. Think about it with me. The International Space Station doesn't stop in empty space. It plummets toward Earth almost 4.3 meters every second, and it misses the ground, and it misses again and again. 16 times a day, it makes a full orbit around the planet, never, not even once, touching the ground. It's not the absence of gravity up there. It's falling. That's all. At the end of this video, I'll tell you about a man who felt this alone, for the first time in human history, with no guarantee that his body would withstand it, and with no one to ask afterward. What you heard seems contradictory. How can you fall without ever getting anywhere? Every fall your body takes has an end. You fall out of bed, you fall down the stairs, and at some point the floor catches up with you. It hurts, but it ends. Orbital physics doesn't have that kind of ending. Think of a bullet fired horizontally. It goes straight, but gravity pulls it down all the time. So the trajectory is curved and it ends up hitting the ground farther ahead than if you had just dropped it from your hand. Now increase the speed of the bullet. It goes farther before falling. Increase it again, even farther. This is where it gets weird. There is a speed at which the bullet falls as fast as the Earth curves beneath it. In other words, the ground moves away at exactly the same rate as the object descends. The result is not a fall that ends. It's a fall that chases a target that's always escaping at just the right speed. And that's not a metaphor. It's the literal definition of orbit. The moon has orbited Earth for billions of years, just as Earth orbits the sun. And a football field-sized station with people inside is doing this 400 kilometers above you right now as you listen to this sentence. Ask anyone you want, why do astronauts float? The answer you'll probably hear is, because there's no gravity in space. That's wrong. Deeply wrong. At 400 kilometers above the ground, Earth's gravity still pulls with about 90% of the force it does down here, where you're sitting right now. If gravity really disappeared up there, the International Space Station would shoot straight out into deep space and never come back. The fact that it keeps orbiting the Earth every 90 minutes is proof that gravity is still there, almost completely intact. But wait, maybe it's the vacuum then. No air, no resistance. Is that why they float? That's not it either. A vacuum doesn't cancel out weight. A stone released in a vacuum still falls. Galileo had already shown this 4 centuries ago, and the Apollo 15 astronauts repeated the experiment live on the moon in 1971, dropping a hammer and a feather at the same time. Both fell together at the same instant because there was no air to slow down the feather. A vacuum doesn't prevent falling. A vacuum only prevents friction. So maybe it's the distance, too far from Earth for gravity to reach. That's not it either. Gravity never stops. It just weakens with the square of the distance, but it never reaches zero. The moon itself, 384,000 kilometers away, still feels Earth's pull strongly enough to stay trapped in orbit for billions of years. It's not the vacuum. It's not the distance. It's not the absence of gravity. It's falling. That's all. And it's the only answer that almost no one gives right away. Go back to the elevator. That second when it drops before it stops. In that second, your body and the elevator floor fall at the same speed. That's why for a moment you don't feel the weight of your own feet. It's not magic, it's physics. There's no speed difference between you and the surface supporting you. Both accelerate toward the ground at the same rate. Now picture this elevator without cables, falling endlessly and never hitting the ground, as the building curves away at the same speed. You're not floating, you're falling. That's exactly what happens inside the International Space Station. The station is falling. The astronauts inside it are falling. The tools floating in the air are falling. The water that escapes from a bottle falls. Everything falls together at the same acceleration, so nothing presses against anything. There is no difference in speed between you and what is around you. There is only shared free fall. The sensation your stomach feels for half a second on a roller coaster is the sensation the human body experiences, continuously, for months during a mission up there. No pause, no relief. The body never gets the signal that it has reached the ground, because technically it never does. There's a passage in the Feynman Lectures on Physics, Volume 1, Chapter 7, the chapter on the theory of gravitation, where Feynman uses almost the same scene to explain the moon's orbit. He doesn't mention the ISS, of course, since it didn't exist when he lectured at Caltech in the early 1960s. But the reasoning is identical. He asks the student to imagine a stone thrown horizontally. The harder you throw it, the farther it goes before falling. And at some point, according to him, the stone's trajectory stops being a fall that ends and becomes a fall that circles the entire planet, eternally chasing ground that is always curving away at the same speed as the fall. I always thought it was strange that this idea, as simple as throwing a stone, Took almost 300 years for someone to actually confirm outside of theory, because the reasoning that Feynman was recycling in the classroom wasn't his own. It belonged to another Englishman, 2.5 centuries earlier. This is where it gets strange again. If falling together with everything around you makes gravity disappear for you, is gravity real, or is it just a frame of reference illusion? It was exactly this question that kept another physicist awake more than 200 years after Newton. In 1907, while working as a clerk at a patent office in Bern, Switzerland, Albert Einstein had what he himself called, decades later, the happiest thought of my life. He imagined a person falling from the roof of a house and realized that during the fall, this person would not feel any weight at all. For that person, momentarily, gravity simply would not exist. This insight became the foundation of general relativity. Gravity and free fall are locally indistinguishable. You can't do an experiment inside a closed box in free fall and find out if you're being pulled by a planet or simply floating far away from any mass in the universe. The two situations look exactly the same from the inside. This complicates the story you just heard because it means that the ISS astronauts are not cheating gravity. They are, in a very real way, experiencing what Einstein described as a local absence of weight, even while surrounded by 90% of Earth's gravity. Modern physics still debates the exact limits of this equivalence principle on very large or very small scales. But in low orbit, it has been confirmed every single day for more than 60 years of spaceflight. Now, the scene I promised at the beginning. Back to Newton. Around 1685, he drew a diagram that would become famous. A giant cannon on top of an impossibly tall mountain, above any atmosphere. He imagined firing a cannonball horizontally. With little gunpowder, it falls nearby. With more gunpowder, it falls farther. And with enough gunpowder, he calculated, the cannonball would never actually fall. It would follow the curve of the Earth at the same speed that gravity pulls it down, and would keep coming back to hit the mountain from behind forever in a closed orbit. This illustration was published in the book A Treatise of the System of the World, which in Portuguese would be something like Tratado sobre o Sistema do Mundo. But Newton never saw the book printed. He died in 1727. The treatise was only published a year later, in 1728, organized by his colleagues from his manuscripts. He designed with pencil and geometry a machine that would take more than 240 years for someone to actually build. It was the Soviet Union that built it. On October 4, 1957 in Baikonur, Sputnik 1 became the first object made by human hands to actually accomplish it. Newton's cannon, a 58-centimeter metal sphere falling forever around the planet, never touching the ground. 4 years later, on April 12, 1961, a man did the same thing, but with his body, not with metal. Yuri Gagarin, 27 years old, took off alone aboard Vostok 1 and spent 108 minutes making a complete orbit around the Earth in free fall the entire time. Before the flight, some of the Soviet scientists had genuine fears. No one knew for sure if the human brain could withstand minutes at a time in weightlessness. There was real concern that he might lose the ability to think clearly or even to swallow properly. Gagarin took off with no guarantee that he would return with his mind intact. He came back laughing. He later described the sensation as strangely calm, not like a violent fall, but like a gentle floating. His body had just experienced, for the first time in the history of our species, what Newton had only been able to draw on paper. Now, take a step back. Think about it with me. The ISS is not the exception, it's the rule. The moon has been falling around the Earth for billions of years, at an average distance of 384,000 kilometers, taking about 27.3 days to complete one orbit. The Earth, in turn, falls around the Sun at almost 30 kilometers per second, more than 100,000 kilometers per hour, and takes 365 days to complete this giant orbit. You don't feel any of this, but your body is, right now, hurtling through space at a speed that would make the ISS seem like it's standing still. It doesn't end there. The sun is also falling. It orbits the center of the Milky Way at about 220 kilometers per second, and it takes between 225 and 250 million years to complete a single revolution. Such a long period that astronomers have called it a cosmic year. The last time the sun passed through the exact point where it is now, dinosaurs didn't even exist yet. The next time it completes this orbit, more than 200 million years from now, no one can say what shape the continents will have, or if there will be anyone around to notice the coincidence. And even entire galaxies fall. The Milky Way is, at this very moment, falling toward a structure called the Great Attractor, a concentration of mass hundreds of millions of light years away, pulling an immense number of galaxies in the same direction. There is no single object truly at rest anywhere in the observable universe. Everything that has mass is falling towards something bigger. The difference between you sitting in a chair and an astronaut floating on the ISS isn't that one is falling and the other isn't. In your case, the ground is falling with you too. It's just that at such a similar speed that you both seem to be standing still in relation to each other. Gravity never took a day off. It just made you seem motionless. I'm not going to pretend I completely understand what that does to the mind of someone who spends months up there, but I started to think differently about something much more down to earth, the feeling of having no ground beneath your feet. Recall the last time your life changed suddenly. A job that ended, a relationship that cooled off, a city you had to leave. You probably experienced it as a fall, as if the ground had disappeared beneath you and nothing was holding you up. Orbital physics suggests another interpretation, stranger and, I think, more generous. Maybe you never had any solid ground at all. Maybe none of us ever did. The entire planet is in free fall around the sun. The sun is in free fall around the galaxy. You were born, live, and will die within a continuous fall that began billions of years before you and will continue billions of years after. The stability you feel in the morning, having coffee, with your feet planted on the ground, is an illusion of scale. A fall so gentle, so synchronized with everything around you, that your body decided to call it standing still. There isn't a single fixed point in the entire universe for you to compare and say, this is where everything starts to move. Everything is already in motion. It always has been. Think about that the next time you feel the ground disappear beneath you. Maybe that's why life never seems to have solid ground. Not because you're doing something wrong, but because falling continuously without ever hitting the bottom is the natural state of everything that exists. From a station 400 kilometers up to an entire galaxy millions of light years away. Truly standing still would be the exception. Falling is the rule. If you prefer to understand the fall rather than just blindly trust that the ground will hold you forever, you're already thinking like a physicist. And that alone already sets you apart from those who look at the sky without ever asking why. Let's return to the opening question of this video. The station is falling. Now, while you finish listening to this sentence, it fell while you breathed. It will keep falling after this video ends and tomorrow and a year from now. Slowly losing about 100 meters of altitude per day because of the extremely thin atmospheric drag up there, being boosted back up every few weeks just to keep falling properly. I started to notice this feeling in small parts of my life. The jolt of turbulence on a plane, the moment before the elevator stops, that second in a dream when you feel like you're falling and wake up startled. Remember that next time it happens. I no longer see those moments as failures of my balance. I see it as a quick and free reminder of what Newton drew on paper more than 300 years ago, and no one before Gagarin had truly felt it alone, with no guarantee of return. Maybe the most elegant thing in the universe is exactly this. The most violent fall there is, people plummeting at 27,600 kilometers per hour for more than 2 decades without stopping, felt from the inside as the most absolute calm the human body has ever experienced. You don't see the mechanism, You only see the piece it produces. You don't float, you fall. And maybe the question worth taking with you isn't how to stop falling, because no one ever stops, anywhere in the cosmos. But what changes when you stop calling it a fall and start calling it simply being alive? Think of two people. It could be a dance, it could be an orbit, it could be a relationship. It doesn't matter what name you give it. With two, there's a pattern. It comes full circle, it repeats, forever in the same way, predictable down to the last decimal place. Now put a third one in there. No matter how carefully you calculate, the system never repeats exactly the same path twice. This isn't about human relationships, it's about physics. And it's the same laws that Isaac Newton wrote over 300 years ago. Two masses attracting each other under universal gravitation have an exact, closed form, eternal solution. You add a third body in the middle, another planet, another moon, another star, and the same math with the same perfect laws simply breaks down. It breaks down. It's not due to a missing formula, it simply doesn't exist. And the way science found this out is just as embarrassing as the discovery itself. A mathematician won an international prize in 1889 for solving this problem. He was wrong. Correcting the mistake cost more than the prize he had just received. I'm going to tell you this story all the way to the end because it was right there, while trying to fix an embarrassing paper, that physics accidentally stumbled upon one of the most important ideas of the 20th century. Remember this sentence, it will return. Knowing the rules doesn't guarantee you can predict the future. This is where it gets weird. The law doesn't change, the force doesn't change. It's the exact same equation, the same universal gravitation that Newton published in 1687 in the book Principia. So why is that? Two things attracting each other has been a solved problem for over 3 centuries, and three things attracting each other still doesn't have a general solution today? Think of a seesaw with two people. It rocks back and forth, always in the same rhythm. You can calculate exactly where it will be an hour from now or even a year from now. Now put a third person on the seesaw in any position. Suddenly, no one can predict the movement anymore, except for a few seconds ahead. Not because people became less accurate, but because the system, mathematically, no longer has a closed-form solution. Have you experienced this without calling it physics? A group of two people has an intense dynamic. A group of three changes configuration all the time. Two team up, one is left out, then it switches again. A family with 2 children has a routine. A family with 3 has constant negotiation. The number 2 is stable. The number 3 is structurally a whole different category of problem. And this applies both to physics and to your living room. Your first instinct, and that of pretty much everyone who hears this for the first time, is to think it's just a matter of computing power. But wait. Today, the most advanced supercomputers on the planet simulate trillions of operations per second. And even so, no one can accurately predict, a long time from now, where 3 bodies will be. It's not uncommon hardware. The problem isn't calculating fast enough. Second instinct, it must be something about mass, weight, or scale. Planets are too heavy, that's why it got complicated. But wait, 3 grains of dust, no matter their size, under the same law of gravity, show exactly the same behavior. It's not about how much it weighs, it's about how many things there are. They're pulling on each other all at the same time, all changing each other's positions at every moment. Third instinct. So you just use more decimal places, more precision in the initial measurement, and the prediction gets better. But it doesn't really get better, it just postpones the error from a tiny measurement at the start, too small for any instrument to detect, which grows exponentially over time. You can gain more decimal places of precision. Today, tomorrow, on the right time scale, they're not enough anymore. And the fourth instinct, the most stubborn one, but there's a mathematical formula that solves this, so it's technically solved, it exists. 1. I'll tell you about it in a bit and explain why it doesn't help much at all. In practice, it's not a lack of computers, It's not a lack of precision. It's not a lack of genius. It's the very structure of the problem that resists. Think of one of those compasses you use to draw circles at school. You stick the sharp point in a fixed spot, spin the other end, and the result is a perfect, closed, exact circle, just like the first and the thousandth time you draw it. Two masses attracting each other do exactly that. One of them acts in practice as the fixed point, and the other draws a perfect ellipse around it, forever. It's Kepler's first law, mathematically deduced by Newton. Clean, closed, eternal, like a vinyl record that plays the same track forever, never skipping. Now imagine a compass where the fixed point is also being pulled by a third magnet, somewhere out of your sight, moving on its own. The point that was supposed to stay still starts to slide. The line that was supposed to close the circle never closes again. It keeps being drawn point by point, following the same physical laws, with no chance, no randomness, and yet it never repeats the patterns, exactly the same line twice. That's the heart of the three-body problem. There is no fixed point. The three objects pull on each other all the time, and each pull changes the position that will determine the next pull. The line never closes, the music never repeats the chorus, and the longer you wait, the further today's prediction gets from tomorrow's actual position. The first person to run into this again was Newton himself. In 1687, in the Principia, he solved the case of two masses with an elegance that is still taught today without changing a comma. Excited, he tried the next obvious step: the Earth, the Sun, and the Moon. Three real bodies actually moving in the sky above him. He needed this for a very practical reason. Accurate lunar tables were, at the time, the tool that ships used to calculate their position in the middle of the ocean. Newton spent years on this, in the 1690s, redoing the same calculations over and over again in Cambridge, according to the account of the astronomer Edmund Halley, his close friend. Newton confided that this specific problem, the one about the moon, was the only one that actually kept him up at night and gave him headaches. It wasn't gravity itself, it wasn't the distant planets, but it was exactly this: three ordinary bodies pulling on each other. He never finished solving it. Almost a century later, Leonard Euler, in 1767, found some very specific configurations where three aligned bodies continue to move in a predictable way. 5 years later, in 1772, Joseph Louis Lagrange found another case where three bodies form a perfect equilateral triangle, rotating together also in a predictable way. They were beautiful exceptions, rare, mathematically honest, but they were not the general answer. In the common case, Newton spent years on this, in the 1690s, redoing the same calculations over and over again in Cambridge, according to the account of the astronomer Edmund Halley, his close friend. Newton confided that that specific problem, the one about the moon, was the only one that actually kept him up at night and gave him headaches. It wasn't gravity itself. It wasn't the distant planets. It was exactly this one: three ordinary bodies pulling on each other. He never finished solving it. Almost a century later, Leonard Euler, in 1767, found some very specific configurations where three aligned bodies continue to move in a predictable way. 5 years later, in 1772, Joseph Louis Lagrange found another one: three bodies forming a perfect equilateral triangle, rotating together also in a predictable way. They were beautiful, rare, mathematically honest exceptions, but they weren't the general answer. In the common case, the problem remained open. But here the subject gets more sophisticated than just, there is no solution, period. In 1912, the Finnish mathematician Carl Sundman published a real answer: an infinite, convergent mathematical series that, in principle, gives the exact position of the three bodies at any moment in time, forever. Technically, he solved the three-body problem. But wait, before you celebrate, stop and calculate this carefully. For this series to actually become useful, with the precision that real astronomy requires, the calculations show that you would need to add not 8 million terms, but a number of terms so large that, when written out in full, it has about 8 million digits. No computer today, or in any foreseeable future, can process that in any useful way. Sunman technically settled the mathematical question and at the same time changed almost nothing. In practice, it's a rare kind of real victory on paper, useless at the telescope. To this day, mathematicians debate whether that counts as truly solving the problem, and the most honest answer is a matter of definition. What do you mean by solving? Knowing the rules doesn't guarantee you can predict the future. Technically, you're calling it the number of terms. You're calling it the international prize. Three of Europe's greatest mathematicians, Charles Hermit, Karl Weierstrass, and Gustav Mittag-Leffler, organized an international prize. Whoever could mathematically prove whether the solar system was infinite would win the prize. Henri Poincaré, a 35-year-old French mathematician, submitted a study in 1888 on exactly this problem, the three-body problem. The committee was impressed and described the work as the work of a mathematical genius, the kind of mind that opened a new era in celestial mechanics. Poincaré won. The article was prepared for publication in the journal Acta Mathematica, with the intention of being printed right on the king's birthday. However, while reviewing the proofs, the assistant editor of the journal, Lars Edvard Fragman, came across a passage he couldn't understand. He wrote to Poincaré asking for clarification. It was July of 1889. Poincaré went back over his own reasoning to try to explain the passage and realized, on his own, in silence, that he had made a serious mistake. He had assumed that the trajectories of the three bodies would, over time, settle into relatively simple and almost closed curves. It wasn't true. Redoing the calculation, he found the opposite. The trajectories crossed and intertwined infinitely in such a complex way that no simple formula could describe it. The journal had already printed the article. It had already been distributed to subscribers all over Europe. Poincaré urgently requested that the entire print run be recalled and destroyed. He personally paid to reprint the corrected version, and the amount he spent was greater than the entire prize he had just won. The corrected version was released in 1890. And that mistake, discovered by accident by a confused editor reviewing typographical proofs during a European summer, is now recognized as the first mathematical description of what we call chaos. Topics where tiny differences at the beginning turn, over time, into completely different results. 74 years before the meteorologist Edward Lorenz formulated his most famous version of the same idea, Poincaré had already stumbled upon it while trying to fix his paper, embarrassed and in a hurry during a rainy summer in Paris. That sounds like a story about a mathematician locked in a room. It's not. The exact points that Euler found in 1776 and Lagrange found in 1772, those rare configurations where three bodies behave in a predictable way, became, centuries later, a real tool for space engineering. Each pair of large bodies in space, like the Sun and the Earth, generates 5 of these gravitational equilibrium points around them, called Lagrange points. In the Sun-Jupiter system, 2 of these points have been accumulating rocks for billions of years. More than 15,300 asteroids named Trojans had already been cataloged there by October 2025. The first of them, called 588 Achilles, was discovered in 1906. They have been trapped in that specific balance since the early days of the system, about 4.5 billion years ago. In the Sun-Earth system, one of these points, called L2, is 1.5 million kilometers from Earth, 4 times farther than the Moon. That's exactly where the James Webb Space Telescope is today. But is a misleading word. But L2 isn't really a stable place. The telescope orbits around the point O in a trajectory that varies between 250,000 and 830,000 kilometers away from it. And 830,000 kilometers away from it. It uses propulsion bursts to correct its course every few weeks, or else it would drift away. The same chaos that Poincaré found by accident back in 1889. It is today the practical reason why the most expensive telescope ever built by humanity needs constant orbital maintenance. Alone, 1.5 million kilometers from home. And the problem doesn't stop at three bodies. Our entire solar system, the sun and 8 planets, is basically a 9-body problem, and it suffers from exactly the same issue. In 1989, the French astronomer Jacques Lascar published in the journal Nature a calculation that showed that the inner planets of the solar system have chaotic orbits. Stop and calculate that number carefully. Stop and think about it. That margin of error in measuring Earth's exact position is enough to make it impossible to predict where it will be a little over 100 million years from now. Not because there's a lack of data, but because on that timescale, the calculation itself stops making sense. You don't need 3 planets to feel that firsthand. You feel it every time making plans with 2 people is simple, but the same plan with 3 turns into endless negotiation. Setting up a meeting with 1 person is just one message. Making plans with 2 takes coordination. Making plans with 3 is, suddenly, 7 different versions of time, place, and who cancels first, changing even minutes before leaving the house. It's not your lack of organization. It's not a lack of planning. It's the same structure that stumped Newton. Each new person who enters the equation doesn't add complexity. They multiply it. 2 people deciding something together form a closed, predictable system. 3 people deciding something together form a system where each person's decision changes in real time what the other 2 will decide next, just like each body in space changes the trajectory of the other 2 at every moment. In the morning, when 3 people try to use the same bathroom, the same car, the same coffee maker at the same time, and everything always seems to go wrong in a new way, that's not bad luck. It's the same mathematics that Poincaré found while trying to fix an article. A trip planned by 3 friends where the destination changes 4 times before it even gets off the ground is, structurally, the same kind of system that no supercomputer can predict beyond a certain point. That should make you feel relieved, not frustrated. You're not bad at predicting the behavior of groups of 3 or more people. No one is. Not even Newton was. The entire universe, with the most precise laws that exist, can't do it either. I started looking at the sky differently after I understood that. I no longer see a perfect clock turning up there, predictable down to the last decimal place. I see billions of 3-body relationships or more, each one writing, right now, a line that will never repeat itself in exactly the same way again. The entire solar system is, deep down, a giant many-body problem just pretending to be stable on the short scale of a human lifetime. In 100 million years, no one, not physics, not Newton, not even the most advanced supercomputer that will ever be invented, knows exactly where the Earth will be. Determinism is not the same thing as destiny. The laws are perfect. Even so, the future remains open. Knowing the rules doesn't mean you can predict the future. There is a way to steal energy from the universe without paying anything for it. No engine, no fuel, without spending even a single watt. You must have heard this phrase 1,000 times. There's no such thing as a free lunch. Everything has a price, always. Energy doesn't come out of nowhere. That's not an opinion, it's a law. The most robust law that physics has ever tested. But on March 5th, 1979, a NASA probe the size of a small car skimmed past Jupiter and left there flying more than 36,000 kilometers per hour, faster than when it arrived. No engines running, not a drop of fuel burned. Think about that. That shouldn't be possible. Here's the odd part of this story. She didn't steal energy out of nowhere. She stole it from someone. She stole it from Jupiter. And Jupiter didn't even notice. There's no such thing as free energy. There is borrowed energy. That sentence will make total sense in a few minutes. The law of conservation of energy says one simple thing. You don't create energy and you don't destroy energy. You only transform it, or transfer it from one place to another. Whenever something gains energy, something else has lost exactly the same amount. No exceptions, no discounts, no silent letters. In no experiment, anywhere in the observed universe, has a violation of this law ever been measured. So how does an 825-kilogram probe skim past a planet without firing any engines and come out of there with 10 kilometers more speed? Where did that energy come from? Think this through with me. You push a shopping cart, it moves while you push it, and it stops as soon as you let go. You kick a ball, it rolls until friction eats up all the energy. In your whole life, you've never seen anything speed up on its own, out of nowhere, without someone paying for it. Why would it be any different out there? In a vacuum, near a planet? The first answer most people give is, it must be Jupiter's gravity pushing the probe forward, like a real slingshot. But wait, gravity alone can't do that. It pulls the probe in when it arrives, and pushes it out when it leaves, in exactly the same proportion. If Jupiter were standing still in space, not moving, the probe would leave the encounter at the same speed it entered. Not even 1 km more. The second answer is, then it must be some kind of geometry trick. The trajectory bends in such a way that it creates speed out of nowhere. But wait, geometry doesn't create energy. You can only change the direction of something using geometry. You can't change its speed without applying a force that comes from somewhere real. The third answer, the most common one, must be measurement error or an effect too small to matter. But wait, NASA's engineers measured this speed gain with meter-per-second precision over 4 decades ago, and it matches exactly with the mathematical prediction made before it happened. It's not a mistake. It's physical, it's measured, it's real. This is where it gets strange, and also where it gets simple. Think this through with me. A tennis ball and a train. You're standing on a platform holding a tennis ball, and a bullet train is coming toward you at 100 km/h. You throw the ball at the train, it hits the front and bounces back. But it doesn't return as fast as it was thrown. In a perfectly elastic collision, it comes out with its original speed plus twice the speed of the train. It comes flying back at almost 300 km. Where did the extra speed come from? From the train. The train lost an infinitesimal fraction of its own speed, something so small that no instrument on board would ever detect it. And that fraction transferred to a 60-gram ball made a huge difference to the ball. Now swap the ball for a space probe. Swap the train for Jupiter, a planet with enough mass to swallow 1,000 Earths inside it. The probe doesn't crash into Jupiter. It curves around it, entering from one side and exiting from the other in the same direction as the planet's orbital movement. The mathematical result is identical to that of the ball in the train. The probe steals a bit of Jupiter's momentum. The planet loses an amount of speed that's too small for any instrument to measure directly. The probe gains a huge amount because the difference in mass between the two is enormous. Stop and calculate. The difference in mass between the probe and Jupiter is on the order of 10 to the 24th power. 1 followed by 24 zeros. It's not mere disproportion. It's a whole different category of thing. It's the same symmetry as you lightly pushing a moving train and the train not even registering that you existed. It's not magic. It's momentum transfer. Pure Newtonian mechanics, tested hundreds of times since then. There's a passage from Feynman that helps explain why this law is so ironclad. Chapter 4 of the first volume of the Feynman Lectures on Physics, published in 1963. The chapter about conservation of energy. He begins by telling the story of a mother and her son, a boy named Dennis, with a handful of toy blocks. She counts the blocks every single day. Sometimes he hides them behind the bookshelf. Sometimes he throws them out the window. Sometimes they fall into another child's toy box. And yet, if she knows how to weigh the bathwater, measure the dust, check behind every piece of furniture, the number always matches. 28 blocks. Always 28, no matter how many strange places he has hidden them. Feynman used this story to explain something uncomfortable. No one knows for sure what energy is. There isn't a physical thing you can hold in your hand and call pure energy. What exists is a number, a quantity that you calculate in different ways for each situation, and it always matches. It doesn't matter how many strange forms it takes along the way. The probe's extra energy didn't come from a hidden block behind the shelf. It came from a specific place, from something that already exists in the world. The orbital movement of Jupiter around the Sun. The number matches, it always matches. This is where it gets weird again. Because there were people who heard this story back in the 1960s and got really worried about Jupiter. In 1965, a graduate student named Gary Flandreau was doing summer work at the Propulsion Laboratory. At NASA's Jet Propulsion Laboratory, he calculated thousands of possible trajectories and discovered that the outer planets, Jupiter, Saturn, Uranus, and Neptune, would align in a rare way at the end of the 1970s. An alignment that only repeats approximately every 175 years. A local Pasadena newspaper published a story about the discovery, mentioning that the probe would gain speed by stealing energy from Jupiter's orbit. A group of students read that and officially founded the Pasadena Society for the Preservation of Jupiter's Orbit. Real people protesting against the idea of messing with the orbit of the largest planet in the solar system. The good news, they didn't need to worry. The bad news, for those who like a twist, technically, they weren't wrong about the mechanism. Jupiter really does lose orbital energy with each flyby. The whole issue is the scale. To move Jupiter's orbit in any measurable way, you would need billions of consecutive flybys, all pulling energy in the same direction for a period longer than the age of the universe itself. The effect exists. It's just too small to be anything more than a philosophical detail. But the person who first saw this mechanism in the numbers wasn't a famous physicist in a trendy lab. It was a graduate student named Michael Minovich, doing summer work at the Jet Propulsion Laboratory in 1961 at UCLA. His original task was to solve, using the fastest computer available at the time, the IBM 7090, a trajectory problem that another researcher at the lab couldn't figure out. Minovich solved the official problem. And then on his own, without anyone asking, he kept working on the equations. He was trying to find a solution to the classic three-body problem, the question of how three objects move under each other's gravity, a problem so difficult that Isaac Newton himself said it made his head hurt. In August 1961, typing the report on a typewriter, with mathematical symbols drawn by hand because the machine didn't have those characters, Minovich showed that a probe passing close to a moving planet could steal a slice of that planet's orbital energy without using any fuel. At the time, no one had yet used this idea to plan a real mission. The first time this was tested in space was in December 1973, when the Pioneer 10 probe passed by Jupiter. The physicist James Van Allen, in an article published in 2003 in the American Journal of Physics, calculated that the heliocentric speed of Pioneer 10, its speed relative to the Sun, not to Earth, jumped from 9.8 to 22, was transformed during the flyby, multiplying the probe's kinetic energy by a factor of 5.2. No extra engine, just Jupiter and the math that Minovich had hand-drawn 12 years earlier. It was Flandreau's calculation about the rare alignment of the planets combined with Minovich's math that made what would come next possible. To launch in 1977 a probe that would visit 4 planets, using each one as a stepping stone to the next. That probe was called Voyager. On March 5, 1979, Voyager 1 passed within 348,000 kilometers of the center of Jupiter, closer to the planet than the Moon is to Earth. On board, no one would feel anything unusual. No acceleration, no jolt, just a continuous sensation of falling, because that's exactly what was happening. Free fall all the time, balanced by enough lateral speed to never hit the target. She rushed in, made the turn around the giant planet, and came out having stolen about 10 kilometers per second of extra speed for free. Jupiter in return slowed down in its own orbit, losing about 10 to the minus 24 kilometers per second, a number so small that there is no instrument, not today nor ever, capable of directly measuring that loss. It can only be calculated. Take a step back now, because this little trick became the backbone of almost all exploration of the outer solar system. Think about that. Without Jupiter's slingshot, Voyager's trip to Neptune would have taken about 30 years. With it, it took 12. With the Cassini probe launched in 1997 towards Saturn, it was too heavy for a single flyby to handle. So the engineers first sent it into the inner solar system, stealing energy twice from Venus, once from Earth, and one last time from Jupiter, until finally it had enough speed to reach Saturn, almost 7 years after launch. The Bepi-Colombo probe, on its way to Mercury, is now doing the opposite. It uses 9 gravity flybys to gradually lose speed, because falling toward the sun is easy. The hard part is arriving slowly enough not to fly right past. This idea of using a planet to slow down instead of speeding up was born in the early 1970s. It was born when the Italian mathematician Giuseppe Colombo from the University of Padua calculated that the Mariner 10 probe could encounter Mercury repeatedly every 176 days using Venus for a gravity assist along the way. And Voyager 1, that same probe that stole energy from Jupiter in March of 1979, never stopped moving away. In August 2012, it crossed the heliopause and became the first object made by human hands to leave the space dominated by the sun and truly enter interstellar space. Today, while you watch this video, it is more than 25 billion kilometers from Earth, traveling at almost 61,000 kilometers per hour. Stop and calculate. A radio signal traveling at the speed of light, the fastest thing there is, takes more than 23 hours to reach Voyager 1 today, more than a whole day, just one way. In November of this year, it will pass the 1 light day mark from Earth, the first time anything built by humans has ever gone this far. None of this would have been possible with the fuel it carried in its tank back in 1977. None of this would have been possible without borrowing energy from planet to planet along the way. There is no free energy. There is borrowed energy. And the more I think about it, the more that phrase seems to apply to things that have nothing to do with space probes. Think about the last time someone helped you in a way that seemed to cost them nothing. A teacher who gave you an extra 10 minutes of attention after class without complaining. A friend who listened to you on a bad night without asking for anything in return, without even seeming tired of it. A father or a mother who gave up a whole night of sleep and the next day acted as if nothing had happened. It's not luck, it's generosity that borrowed energy from somewhere you didn't see. Someone paid a price for that. But just like Jupiter, that person was too big or too generous for you to feel the weight of their loss. The energy came from somewhere real. It's just that the place was big enough to absorb the loss without cracking. It's not dishonesty to pretend it didn't cost anything. It's not a lie, nor an illusion, nor luck. It's scale. The same physics that makes Jupiter give up speed without noticing is the physics that makes someone give up time, attention, patience, without it ever showing up in their account. And maybe that's why we confuse true generosity with magic. Because, seen from afar, on the wrong scale, it looks exactly like that. A few billion years from now, the sun will swell up, swallow Mercury, maybe Venus, and the inner solar system will become unrecognizable. Jupiter will probably stay almost exactly where it is, having given up over centuries of human probes flying past, such a tiny bit of speed that not even geological time will be able to register the difference. I started looking at the night sky differently after understanding this calculation. I no longer see Jupiter as a stationary point of light up there. I see a giant planet that, without realizing it, has already lent a piece of itself to almost every probe humanity has sent to the outer solar system and will never miss it. There is no free energy. There is borrowed energy. And maybe the most beautiful thing in the universe is this, that even the biggest, coldest, most indifferent things give up a little piece of themselves to push something smaller, just a bit further. Not by choice, by physics. But the result in the end is the same. Think this through with me. Have you seen the moon's far side? Not a picture from a space probe. With your own eyes on any given night, ever in your life? The answer is no. And it's not just you. It's your whole family. It's all your grandparents. It's their grandparents too. In about 4.5 billion years of the moon's existence, no human being has ever laid eyes on its far side. Until 1959, when a Soviet probe finally went around and photographed what no one had ever seen before. Now think about something even stranger. That's not luck. It's not a coincidence. It's not the moon hiding anything on purpose. It's pure physics. And it would happen with any moon, around any planet, anywhere in the universe, as long as it was close enough and had enough time. And the reason why this happens is the same reason why, right this very second, your days are slowly but truly getting longer than your grandmother's days. At the end of this video, I'll tell you about a calculation from 1879 that seemed crazy for 90 years, until a mirror left by astronauts on the moon proved it was right. Most people, when they realize that the moon always shows the same side to the Earth, make a small but revealing mistake. They think the moon simply doesn't rotate, that it's static, stuck, motionless in space, just orbiting the Earth like a ball tied to a string. Wrong. The moon does rotate. It rotates exactly once on its own axis every 27.3 days. The thing is, it also makes a complete orbit around the Earth in those same 27.3 days. Both motions, spinning and orbiting, have exactly the same duration. It's this perfect alignment of numbers that makes the moon always show the same face to you. Why do these two numbers match so perfectly? Why does this happen only with the moon, or does it happen anywhere else in the solar system? Has it always been like this, or did the moon rotate differently in the past? And what does this have to do with the fact that, according to your grandmother, the days seemed shorter when she was a child? Because maybe physically they really were. It's not a coincidence. It's not a secret. It's gravitational destiny. Few people know this detail. Even though it's locked, the moon doesn't show you exactly half of itself, not even a millimeter more. Because its orbit isn't a perfect circle and is slightly oval, its orbital speed varies a little. And because of the angle from which you observe on Earth over the months, you can gradually peak it up to 59% of the lunar surface. This side-to-side wobble has a name: libration. It's not enough to actually see the far side, but it's the universe leaving a little crack open, just to remind us that no tidal lock lasting billions of years is absolutely perfect. Imagine two tango dancers in the center of an empty ballroom. At first, one of them spins alone, fast, almost out of control, while the other holds him by the waist and leads the dance. There's no brute force in this process. There's friction, a gentle drag, repeated turn after turn that slowly steals a bit of the dancer's spinning speed with each step. After many turns, hundreds of them, something changes. His spinning stops being free and starts to sync exactly with the rhythm of the dance itself. He stops spinning on his own axis. He starts spinning only around his partner, always facing him, forever. It wasn't a choice, it was friction. repeated long enough until there's no other way out. That's physically what happened to the moon. The ballroom was space. The friction was Earth's gravity deforming still molten rock in a silent tug-of-war. And the dance didn't even last hundreds of turns. According to the best estimates, the moon became locked in less than 100 days after it formed. Friction, repetition, time, a blink of an eye in cosmic terms. It locked almost immediately and never let go again. There's a passage from Feynman that connects directly to this, although he never used the term tidal lock. In the Feynman Lectures on Physics, Volume 1, Chapter 7, The Theory of Gravitation, based on the lectures he gave to freshmen at Caltech between 1961 and 1963, Feynman pauses to talk about tides. He says that before Newton, people already knew that the moon pulled the water in the oceans and caused the tides. That was no secret. What nobody really understood was why the tide rises twice every single day and not just once. He describes this almost laughing at the pre-Newtonian naivety. The common sense of the time imagined that if the moon pulls the water up on one side, there should only be a tide on that side. Feynman explains with the patience of someone who loves to dismantle intuitive errors that the gravity of the moon doesn't simply pull the water upward, it stretches the entire surface, creating two tidal bulges, one facing the moon and the other exactly on the opposite side. I always thought that was beautiful. The same force that seems like a local whim, a tide rising on your beach, is actually an effect on the whole body, the entire Earth being deformed, just a little, all the time. And it's exactly this same tidal bulge, only on the moon and not on Earth, that over time locked it, always facing you. But real physics is more stubborn than it seems. And there's an exception that fooled even astronomers themselves for decades. Mercury, the planet closest to the sun, should be the most obvious example of tidal locking there is. It's stuck to the sun, suffers a brutal gravitational tide. It should have locked a long time ago, always showing the same side, just like the moon does to the Earth. And for decades, that's exactly what astronomers thought. Every time they observed Mercury in the most favorable position, they always saw the same side and concluded locked. Pettengill and Dice in 1865, using the Arecibo radio telescope, showed that they were wrong. Mercury is not locked. It actually rotates exactly 3 times for every 2 orbits it makes around the sun, a ratio of 3 to 2. The reason is that Mercury's orbit is much more elongated, more elliptical, than the moon's orbit around the Earth. When the orbit is not nearly circular, the point of strongest tidal force changes with each pass, and the planet can get locked into a different ratio than the simple lock you might imagine. This doesn't invalidate the rule, it just shows it's more subtle than everything being locked the same way. The exact shape of the orbit decides the final outcome. And that's why scientists still run thousands of simulations of Mercury's history just to understand why it chose this path and not another. This same physics, when applied to other solar systems, is one of the most discussed topics today in the search for habitable planets. Many of the rocky exoplanets discovered orbiting small cool stars, the so-called red dwarfs, are so close to their own star that models suggest that many of them should be tidally locked, with one side in eternal day and the other in eternal night. This is still an active debate among astronomers. Total tidal locking radically changes a planet's climate, and no one knows for sure if this favors or destroys any chance of life there. It's no secret, it's gravitational destiny, but the exact fate depends on the shape of the dance. Now come back with me to 1879 to Cambridge, England. A mathematician named George Darwin, son of Charles Darwin, the one behind evolution, publishes an article in the Royal Society with a calculation that seemed crazy for the time. He argued that the same tidal friction that locks the moon is also slowly slowing down the Earth's rotation. By conservation of angular momentum, or if the Earth is losing rotational speed, that lost spin doesn't just disappear. It is transferred to the moon's orbit, which as a result should be moving away from the Earth year after year indefinitely. George Darwin did not have an easy time in science. Carrying the surname Darwin at a time when his father was still being debated and attacked meant that many people doubted whether the son had his own talent or was just using the family name. He insisted nonetheless. He ran the numbers of Earth's rotation backward in time and calculated that billions of years ago, the moon must have been extremely close to the Earth. Too close, in fact, which led him to propose an idea that is now considered incorrect, that the moon would have split off from a still molten, young Earth spinning too fast. That part we now know is wrong. But the part about tides, friction, and gradual distancing, he got right. For 90 years, there was no way to prove it. Was it calculation? Was it theory? It was just a number on a sheet of paper in Cambridge. Until July 21, 1969, when the Apollo 11 astronauts, before returning to the lunar module, left behind a panel with 100 small mirrors arranged to reflect light exactly back to where it came from. Scientists began firing laser pulses from Earth to that panel and measuring, with an accuracy of just a few centimeters, how long it took for the light to go there and back. Dick and his colleagues, in a 1994 study published in the journal Science, using decades of data from this experiment, confirmed the moon is moving away from Earth by 3.8 centimeters per year. Almost exactly what Darwin's calculation, made 115 years earlier without lasers or computers, predicted should happen. Now stretch that out to the rest of the universe. Pluto and its moon Charon have taken this process to the limit. The two are mutually locked together. If you were standing on the side of Pluto facing Charon, Charon would remain fixed in the sky, suspended, never rising, never setting. On the other side of Pluto, you would never see Charon, not even once in your entire life. It's the ultimate fate of any pair of companions, bodies bound by gravity, given enough time. The two stop spinning freely and start rotating only around each other, always facing each other. It's not just Pluto and Charon. And Io, Europa, and Ganymede, three of Jupiter's moons, have all been locked to the giant planet for billions of years. Europa, in fact, probably hides a liquid ocean beneath its ice crust precisely because of this same tidal friction. Its orbit is slightly pulled by Io on one side and by Ganymede on the other, enough to keep the moon squeezing and relaxing with each revolution, generating heat inside. It's not just about always showing the same face to the planet. Sometimes it's the engine that keeps a world geologically alive inside, even hundreds of millions of kilometers from the sun. And that's what's slowly happening between the Earth and the moon right now. Each tide that rises on your shore steals a tiny, almost imperceptible fraction of Earth's rotational speed and pushes the moon's orbit slightly outward. The result, according to atomic clock measurements confirmed by ancient geological records, is that Earth's day is increasing by about 1.7 to 2.3 milliseconds per century. It seems like nothing. But in rocks from 620 million years ago in Australia, scientists found sedimentary layers formed by the tides of that time, and they show a day lasting 21.9 hours and a year with 400 days. The Earth used to spin much faster than it does today. When it formed 4.5 billion years ago, the day probably lasted about 6 hours. If nothing else happened, physics points to a clear destiny. About 50 billion years from now, the Earth would also become locked to the moon, just like Pluto is locked to Charon. The day would become as long as the month, almost 47 times longer than it is today. But that's never actually going to happen, because long before that, about 5 billion years from now, the sun will run out of fuel in its core, swell into a red giant, and most likely swallow the entire Earth. The dance between the Earth and the moon is a dance destined to never truly end. It will only be interrupted by something bigger before the final step. It's easy to think that truly knowing someone or something is just a matter of time. That if you stay close enough, for long enough, eventually you'll see everything. But the moon is physical proof that this isn't true, not even for the closest, most constant, most observed object in your entire life. You were born looking at the moon. You will die without ever having seen 41% of it, not because it hides on purpose, We've already seen that it's not its choice, it's inertia, it's physics. It's the result of billions of years of silent gravitational friction, but the practical result is the same: intimacy. Even the oldest, the most constant, always keeps a side that you simply will never see. I think that's also true for those who are closest to you, in a way that doesn't have to be sad. There are people you've known for decades and still there's a part of them, a thought, a morning alone, a version of when they were a child that you'll never witness. No matter how much time you spend together, because time doesn't work like that. Truly knowing someone might not mean seeing 100% of them. It's staying in an orbit unstable enough to keep looking at the same side, round after round, even knowing there's always a half you'll only ever imagine. And maybe the strangest part of all this is that this process never stops. Not with the moon, not with the earth, not with you. Each passing day, physically, is just a little bit longer than the day before. Not on the calendar, on the clock. The time it takes for the Earth to spin once on its axis has been increasing year after year, ever since there have been oceans crashing against its shores. You will never feel this difference in your body, but it's happening right now while you're listening to this. I won't pretend to fully grasp the magnitude of this. When I first read about Darwin's calculation, a man sitting in a room in Cambridge in 1879, predicting on paper a phenomenon that would only be confirmed 90 years later. Because of the mirror left by the astronauts, I started to look at the moon differently. Not as something finished, static, completed in the sky, but as a process that's still ongoing. Something that is still happening, too slowly for me to notice, and too fast on a cosmic scale to last forever. The moon you see tonight is not at the same distance, nor does it have the same size in the sky as the moon that the first human being saw, and it won't be the same a million years from now. It is moving away centimeter by centimeter, taking with it a bit of Earth's rotation speed, slowly pulling its days toward a future that neither of them will live to see completed. Because before the dance ends, the sun will turn off the lights in the ballroom. It's no secret, it's gravitational destiny, but it's a destiny that no one will witness all the way to the end. And maybe that's exactly why it's worth looking up tonight. Not to see something finished, but to see in real time the halfway point of a process that lasts billions of years.